Hello, multivariable calculus students. This is Mr. Johnson, and this is the second video for section 10.1. And we're going to talk first about continuity. So, just like in single variable calculus with A, B, and BC calculus, if you have a continuous vector function, just like if you have a continuous Cartesian function, your limit as the variable approaches a value a, let's say, so if t approaches a of your vector function r of t, it will be equal to the function at that value of a. So what we're basically saying here is that as you get close to a value, it's equal to the actual function value, meaning there is no gap or hole in the particular curve itself. Okay, now with that idea of the continuity, the definition of a space curve is a connection between continuous vector functions and the idea of the vector equations that we started with in chapter 9, where we started with lines and being able to write that equation in terms of t. So when we're looking at these space curves, it's just more of a generalization of lines and other curves through space that are defined by components such as f of t, g of t, and h of t. When we look at a vector valued function and a parameter of t, we want to make sure that, similar to how I graphed it in that first video, we're putting in values of t, and in return we're getting these vectors that allow us to trace out and land at one point along the curve, and then we would put in another input value and trace out with a vector and land on the curve. And this allows us, as we do this over and over and over and over again, to get this nice smooth space curve, not only the picture of what it is, but also the path if there was some sort of, let's say, particle moving along that particular space curve. Okay, let's move on to the next page and look at some of these examples. So the first example we're going to look at is one that we should immediately know from last chapter. This particular curve is a line. Now, when we see this right now, it's going to be easier because it's one of the only ones that we've seen. But as we get into more and more of these types of vector functions, we're going to start to forget about some of the things we learned in chapter 9. So when it says describe the curve defined by r of t, this particular curve is a line. So the curve is a line through the point. And again, think back to what we learned in chapter 9. We have our values of our x, y, and z here, our initial point. So through the point 1, 2, and -1, and parallel to the vector. And that's where A comes from. Remember, A, B, and C, the vector that is defining the slope of the line. So that's going to be 1, 5, and 6. Okay, so just again, don't forget the things that we've learned, especially in chapter 9. Even if we get more complex vector functions, just remember the simple ones, okay? All right, for example 4, we're not going to sketch because it's done for us, but I will help you develop the idea of the sketch. Of the curve whose vector function r of t is defined as cosine t, sine t, and t. So let's think back to just, I guess, last year mostly. If t was 0, so if z, which is equal to t, because remember I'm looking in the vector function right here at that third component. So if z was equal to t and it was 0, we are now in the xy plane. So if that was the case, what we have here is x equal to cosine t, sine equal to, x equal to cosine t, y equal to sine of t. And again, I'm looking at my components of the vector function. So maybe I just define this here. So this is x of t and y of t and z of t. Okay, well remember, we already discussed this in the first video. You're going to be getting this nice unit circle right here where z is 0 and x and y define this circle with a center at the origin, radius of 1. Now, if z is 0 at that one moment, because remember z is changing because z is equal to t, we could say that, all right, at time 0, then the vector that's produced here would be cosine of 0, which is x, that's 1, and sine of 0, that's y, that's going to be 0. And of course, we already talked about how z was 0 here. Now remember, we just substituted in a value for t, and in return, remember our vector function gives us in return a vector. That vector allows us to trace out a point from the origin out to, in this case, 1, 0, 0, and we just simply plot a point along the curve. I'm going to make that red. And you can see that we've begun the space curve in this context. Now let's try another one. Let's say that z, which is equal to t, is equal to pi over 2. And I'm picking really specific values so that's easier for us to understand what's going on. Okay, if that's the case, at that moment, we have x of pi over 2, and that's cosine of pi over 2, which is 0, and y of pi over 2, which is sine of pi over 2, and that is 1. So we have this new point. And remember, the vector that's produced by this is 0, 1, and pi over 2, because our x is 0, y is 1, z is pi over 2. That creates a vector from the origin out to this point along our curve, and we simply just plot a point on this particular space curve. Now, if you notice, and this picture I think is really nice versus trying to sketch it by hand, you can see the path of the particle. Now, if you were to look at this from the positive z-axis, if you were to sort of hover over it, you would see a circle. In other words, if you were to look at it from positive z and essentially eliminate the values of z that we're analyzing, and let's say that you had no depth perception to your vision, you would simply see a curve that was in the perfect form of a circle, which is what I was trying to communicate with this very first one. You'll see, even though this is rising up along the z-axis, if you looked at it from this angle, you would see just a simple circle with a radius of 1 centered at the origin. However, as you look at this vector function, since t is the component for z, and that is going to be changing, you're going to start to look at a motion along a circular path, but increasing in nature as you move along this particular space curve. This curve is one that we'll be using a lot throughout the chapter. This is called a helix. And a helix is this type of motion. It's almost like you have a tree trunk and you're watching a squirrel run around and up this tree trunk. It's kind of this path that you're taking along a helix itself. Okay, so anyway, that's the idea behind this particular function, and this one's a very common one that we will utilize throughout the chapter. Okay, let's try example 5. Now, example 5 is a review, so if you want to pause the video and try it and then check, you certainly can. But we're looking at the parametric equations for the line of intersection between the planes. Now, why are we doing this? Well, we're just reviewing from chapter 9 the idea of what this section is in chapter 10. So the intersection here of two different surfaces creates a line, which we now are going to sort of generalize as a space curve. Okay, so if you remember back, we have the first normal vector from the first plane and the normal vector from the second plane, and we're going to cross them. I'm going to pause and write this out. Okay, so what we end up getting here is a vector 5, 11, 7 that is perpendicular to both of these, and since these two are normal to each of the planes, this vector we received is now parallel to both planes. In other words, that vector is parallel to the line of intersection, and therefore we can utilize it for the slope of the line. Now we have to select a point, and we're going to have to wiggle some things around, I think, just because if you look at your two different equations, there really isn't a super obvious one. But I start to look at, 3 minus 2 is 1. So what if x and y are both 1 and z is 0? So if we try it here, we get 1 and 1. That gives us 2 plus 1 is 3. That's perfect. So we're going to use, and again, you could pick up any point that you really want. But I'm just going to try this one, okay? Because it works for me. It works for the two planes there. Okay, the parametric equations then, which is what the problem is asking us for, and then I'm going to give the other equations too, is x equal to 1 plus 5t, and y equal to 1 plus 11t, and z equal to 0 plus 7t. And so if we were to look at our vector function here, so sort of the new terminology we're using, it's r of t, which is equal to 1 plus 5t, 1 plus 11t. Let me clean that up a little bit. 1 plus 11t, and then 7t. And again, the idea here, okay, again, why are we doing the same thing we did last chapter for a moment? Well, it's because we're looking at two different surfaces. So remember, a plane is a really simple surface. It's one of the most simple surfaces we learned. It's the first one we learned. So if you have two surfaces and you intersect the surfaces, you can get a space curve. And in this case, we get a line, which is a pretty simple one, okay? The next couple examples are going to be much more complex with regard to how the surfaces interact. So let's go to the next page. Okay, let's go ahead and start with example 6. I've added some visuals in here that I'll explain in a minute. So with example 6, we're looking at the intersection of two surfaces. And again, we're claiming that this is going to be a space curve. And we just looked at the most simple example that connects to chapter 9. Now we're going to look at more complex examples. So the first one is a vector function that is going to represent the intersection of z equal to x squared plus y squared and z equal to 1. So if you remember back from chapter 9, z equal to x squared plus y squared, this is a paraboloid. I've graphed this over on the right side in blue here, and I'll zoom in on that a little bit. And then z equal to 1, we should know what that looks like. That's going to be a plane, and that plane is going to be parallel to the xy plane. So when we intersect these two surfaces, we get a curve in space, which we call space curve. So here is the sort of the initial. You can see the shadows here. This is the GeoGebra 3D app, which is a great app. You can see the paraboloid here. You can see the paraboloid dips below the plane, and then the plane goes here, and you can see that they intersect. They intersect at this sort of circular spot. I think that I have a better picture here next to it. This is from above. We're looking at sort of from the positive z here, not directly over, but you can see that they intersect at this really nice looking circle. Okay, so we're going to come up with the vector equation for that particular curve in space, that circular curve there. Okay, so let's go back. Oops, sorry. All right, let's start with the idea that, you know, here z is a constant value when you're interacting between these two surfaces. So in the first surface, z equals x squared plus y squared, z can vary. But when you combine it with this pretty simple plane, z equals 1, well, now z is always a constant. So if we were to just simply combine these equations, we get 1 equal to x squared plus y squared. And this is giving us this communication of exactly what we're looking at with regard to that circle that we saw in the graphs that we were analyzing. Now remember, one of the ways, not the only way, but one of the ways that we can take and parameterize the variables here, so come up with a parametric representation, is to use the ones that we have learned in the past, which is x equal to cosine t. Actually, you know what? Let me back up here for a second. Remember how in general we have these two equations when we're looking at circles in a parameter form. Remember, r is the radius. In this case, the radius is 1. So the reason that I'm going with x equal to, actually let's do x of t equal to cosine t, is because the radius is 1 and y could be equal to sine of t. Now, could you flip those and get a similar result? Yes, you could. The path will potentially change, but that would still be a true fact. Cosine squared plus sine squared is equal to 1, and the opposite is also true. So we could flip those around, but let's just go with that for a moment. So if we're coming up with this vector valued function, we've just stated that the first component cosine of t and the second component sine t will produce what we're looking at in regard to the intersection, and z is always going to be 1 in this particular intersection. Now we could add to this that in order to complete that space curve appropriately, really all we need is t values from 0 to 2 pi. We could continue, but all that's going to happen is that you will continue to then retrack the path that we're looking at when those two surfaces interact. And that's our first example. So that's going to be the space curve intersection between those two surfaces. All right, let's take a look at example 7. So here we have a vector function that we're looking for, and it's the intersection of the cylinder x squared plus y squared equal to 1 and the plane y plus z equal to 2. First thing I want to mention is that I want to make sure, without the wording in the problem, if you all see this equation and you are told that it is in space, I want to make sure you know that that's a cylinder, okay? Not only that, but an infinite cylinder that is centered at the z-axis. Now, we've talked about this already. You've already had quizzes on this in Chapter 9. But remember, z is not represented here, which means that z can vary indefinitely. And this is going to be a circle. However, as z varies, that circle can be placed anywhere in space. That's what causes this infinite cylinder. Secondly, y plus z equal to 2. I don't want you to lose track of what we learned in Chapter 9. That's a plane. And yes, we're missing x. All that means is that the vector has a 0 first component. That normal vector would have a 0 first component because there is no x value there. So the normal vector, which we do not need for this problem, I'm just reviewing with you for a moment, is 0, 1, and 1. Okay? It's really important we don't lose track of the things that we learned in last chapter. All right, let's go back to what we're trying to study here. So the question is, what would be a vector function that would represent the intersection? Now you can see by the diagram that it is circular in nature, but it's almost kind of this oval shape. It's sort of on this slant. And so this is going to certainly be a little bit different than what we did in the last example. We are, however, going to look at the x squared plus y squared equal to 1, and we're going to use the same parametric equations for that. I'm going to use x is equal to cosine of t and y is equal to sine of t. Is that the only thing you could do? No, that's what is making it challenging. You could use a number of different parametric representations. The bottom line is that you need to pick something for x and pick something for y for which it's equal to 1. And it's got to be able to vary. So you can't simply just say, well, I'm going to let x be 2 and y be 0. Well, oh no, that wouldn't even work. You could just say x is 1 and y is 0. Yeah, you get an equation that's true, but it's not going to work in terms of the variations that it would produce. So you could say x is equal to sine of t and y is equal to cosine of t. I'm just going to pick this one. Okay, if that's the case, we have y plus z is equal to 2, and if I solve for z, I get z equal to 2 minus y. Now remember, y is equal to sine of t based on our first set of parameters, which means that we could write z equal to 2 minus sine of t. In other words, we've come up with this relationship between both equations in such a way that we've defined them in terms of t. So our first component is cosine of t, and our second is sine of t, and our third is 2 minus sine of t. And that would produce this particular curve of intersection. Now again, similar to the last one, we could have t values from 0 to 2 pi that would perfectly complete that curve. And obviously any more than that would just continue to wrap around that path over and over and over again. Okay, let's try example 8. So 8 says we want to find a vector function that represents the intersection between the two different graphs. Now, again, based on chapter 9, can we visualize them without any kind of aid? So x squared plus z squared equal to 4. Now remember, we just did one that was x squared plus y squared equal to 1, and it was an infinite cylinder. So x squared plus z squared equal to 4 is another infinite cylinder, but the variable that is going to be varying infinitely is y. So that means that this is a cylinder with a radius of 2 that is going to be centered on the y-axis, not the z-axis, the y-axis. What about y equals z squared? Well, that's going to be a parabolic shape. However, x is going to vary, and so you have this infinite parabola that will vary along the x-axis. Okay, and again, we talked about all those items in chapter 9, but I just want you to think about that before I show you this picture. So here is the picture, and I can't really rotate it, it's just sort of stuck there, but you can see, I believe, the light blue cylinder that's centered on the y-axis, and then you can see this infinite parabola that is infinite along the x-axis. Now again, you can see the intersection, I hope. This intersection is this interesting sort of shape that kind of goes along the parabola and where it intersects the cylinder. And that's what we're going to try to figure out is what is the equation, the vector valued equation for that particular intersection. All right, let's utilize the same type of strategy that we had in the previous two. We have a relationship where of an equation that looks as though it's in this trig identity form. The whole idea of sine squared of t plus cosine squared of t is equal to a value like that, except in this case, remember the radius is 2. So we're going to let x be 2 times cosine t, and we're going to let z be 2 times sine of t. Now remember, you can double check by putting those into your equations that you will in fact get 4, because again, cosine squared of t plus sine squared of t is equal to 1, and the 2 is representative of the radius. So again, we didn't have that really as a visual impact on the other two because the radius was 1. All right, if that's the case, then if y is equal to z squared, then y would be equal to 2 sine of t squared, which is 4 times sine squared. Okay, I think we have our vector function. So we have for x, 2 cosine of t. For y, we have 4 sine squared t. And for z, we have 2 sine of t. And again, this is not the only one or representation that we could have. There are some other options for it, but not a lot, because again, we're dealing with a situation where we have a lot of these squared variables, and so due to that, often that trigonometry is what we're going to have to go for, because we're not able to, for instance, if you were to take this first equation, you can't solve for x without getting multiple equations, because remember, if you were to solve for x, you get plus or minus the square root of 4 minus z squared. Well, that's going to be a huge issue. How do you come up with one single variable representation for x if you have two equations? That's something that's going to not be possible. So we're having to utilize the trig identities because of these multiple squared equations. Okay, in this case, again, the t restrictions would be 0 to 2 pi. If you wanted to sort of just travel along that once rather than traveling along multiple times. Okay, let's try one last example, and we'll do some more of these together as well. So in this case, we have our first equation, really ugly looking equation. Notice that it looks kind of like a sphere, except the 9 and the 16 are going to skew that. So it's like an elliptical kind of shape, but spherical as well. And then we have another infinite parabola. And so what I've done is I've just graphed these for you. There's your sort of elliptic spherical combination, sort of a disk, in space. And then here's your infinite parabola, and you can see that there's this intersection of these two surfaces. Now, in this particular case, we're being told that z is greater than or equal to 0. So we could take our equation for z and get plus or minus the square root of 1 minus x squared divided by 9 minus y squared divided by 16. And we are just using the positive version of that because that's what they're telling us here. Okay, if it wasn't for that, our strategy would probably need to change. In fact, we may even have to use some sort of spherical coordinates for this. But since we're able to eliminate the negative here, which I'm going to erase right now, so since we're able to eliminate the negative and just look at the positive values of z, it changes our approach a little bit. Now, here are your two equations, and we do not have the type of situation where we need to pursue the trig identities like we did in the other examples. In fact, we can make up a little bit here unless we don't want to get caught on anything and come up with something that doesn't make any sense whatsoever mathematically. But we could keep things kind of simple, but also take sort of a different strategy. So here's what I'm going to do. I'm going to let x equal t. Now, could x equal something else? Well, of course it could. Could it equal e to the t? Well, not really, because e to the t doesn't have any ability to be negative, which is a problem because we don't want to restrict things beyond what we know could be the value. So you're giving it a value, a parameter, but you want to make sure you don't end up restricting it. Could you let x equal 3t? Sure, why not? Could you let x equal t squared? Okay, well, that's going to get a little bit tricky because now all of a sudden, the only production that x has is positive values if t is squared. So when you're coming up with values here, you have to be kind of careful. Could you let x be sine of t? Well, again, the problem here is that you're now all of a sudden restricting x beyond what the equations are telling us. In the previous equations, we were able to let x and y, or x and z, be trig functions because it worked fully in the equation as a property, as a definition. But here we don't have that. So in other words, we're not being told that there is a specific type of restriction. If you look at your graphs over here, x can be all sorts of things. So if we come up with a parameter that restricts x, we're going to be in some trouble. Okay, so I'm going to let x be t, which is really simple, I know, and a little bit weird, but let's just go with it for now. If that's the case, then y of t is t squared, and that's simply because y is equal to x squared, and if x is t, which we assigned, then y is equal to t squared. Okay, if those two are true, well then z of t will be the square root of 1 minus t squared. Now remember, it's because x is t, divided by 9 minus y is t squared, and we're being told in the equation up here to square it. So we get t to the 4th power, and we divide by 16. This could be our vector valued function. Is it the only one? Absolutely not. There are lots of options here. We're just picking a nice, easy parameter for x so that nothing is specifically restricted. So if you have a parameter in mind, you can ask me and say, hey, would this one work? And we can go through, maybe it will, maybe it won't. It depends on the problem. But remember, the key here is you don't want to pick something for x, for instance, that will allow you to only get a certain type of value, whether that's positive, negative. If it was trigonometry, like sine, well, now x could only be -1 to 1. So you have to be really careful there. Okay, that is it for section 10.1. We added with a little bit of an abstract idea. I hope that helps. We will practice those more. Thank you for your hard work, and the next set we'll start will be on section 10.2. Thank you.